Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll solve a problem on centrifugal pump. In our previous lectures, we have already discussed about the work done about the centrifugal pump, and also we have discussed about the head and efficiency in the centrifugal pump. So based on that concept, let's solve this problem. So here I have taken the question of the internal and external diameter of a impeller of a centrifugal pump. So internal and external diameter is given for a centrifugal pump. That is 200 millimeter and 400 millimeter. The pump runs at 1200 rpm. So speed is given 1200 rpm. The blade angles of the impeller at inlet and outlet are 20 degree and 30 degree respectively. So blade angle also given for the impeller at inlet condition and outlet condition. So water enters the impeller radially. This is one condition. Water enters impeller to the radially in the sense that means we need to consider that alpha equal to 90 degree and that wheel velocity at the inlet condition should be 0. And the velocity of flow is constant. So Vf1 is constant. Determine the work done by the impeller per unit weight of water. So we know the formula of this work done by the impeller per unit weight of water, what we have derived in our previous video lecture. So before solving this problem, so let write down the data given and let try to draw the diagram for this. Okay. So the diagram will be like if you remember already we have discussed during the derivation of work done. So there I told you like this vein will be, if suppose this is the blade or vein, or you can say impeller blade is there. So at inlet condition, the velocity of flow will be like perpendicular to this. Okay. And this is the relative velocity. Okay. This is the velocity of flow or absolute velocity you can say, which is also equal to Vf1 we can write. And the theta will be, this is the angle between this tangential velocity. If you consider this is a tangential velocity, so this is also our u1 at the inlet condition, u1, and this is the arrow mark of this direction, and this is our relative velocity. So relative velocity, we know that when two things are moving simultaneously, we need to consider the relative velocity. So this is the velocity diagram at the inlet condition. Okay. Similarly, at the outlet condition will be like, see, it will move in this directions. So our absolute velocity at the outlet condition, it should be move in this way. Okay. And this is our Vf2. Okay. Vf2, and this is our Vw2, wheel velocity at the outlet condition. Okay. And this is the angle beta. Now in this side, in the outlet condition, at this side, our Vr2, relative velocity will be at this side, Vr2, which makes an angle of phi, and the total length from here to here, that is our u2. So these things already we have discussed previously. So this is about the diagram for the centrifugal pump. Okay, velocity diagram at inlet and outlet condition. Now we'll see what are the data given. What are the data given in this question? So based on that we can solve. Like first line, if you see, the internal and external diameters are given. So I can write internal diameter d1. So that is 200 millimeter. So this one we can convert into meter. So that is nothing but 0.2 meter. Similarly, outer diameter is given. That one we can write d2. So d2 equal to 400 millimeter, and this one we can write, this is 0.4 meter. Similarly, speed of the pump runs at 1200 rpm in the sense that is speed. So that is nothing but n. We can write n, or we can write this is speed in bracket n, and how much is there? This is 1200 rpm. Okay. And the next one is given blade angles at the of the impeller at inlet and outlet conditions of 20 degree and 30 degree. So that is, we can write at inlet condition, the vane angle at inlet condition, this is theta equal to 20 degree. here you can see this is the blade angle, and at outlet condition that will be 5. So this is 30 degree, and water enters the impeller radially. So this statement indicates that our alpha is 90 degree here. Okay, alpha in the sense here it will be at this condition, that is alpha equal 90 degree. So though alpha equal 90 degree, or VW2, sorry, VW1 will be 0. And here already I have written V1 equal to VF1. And what we need to calculate? So we need to calculate the work done of the impeller per unit weight of water. So we know that the work done by the impeller, okay, per unit weight of water, this is nothing but, we know the formula, this is VW2 U2 by G. So here if you see in this equation, except G value, remaining values are not given. Okay, that means we need to find out the value of U2, we need to find out the value of VW2. Okay, so VW2 at the outlet condition. For this you can go in the reverse way. Either you can find out the VW2, then to finding the VW2 we need to go for the outlet condition 10-5. So there we need to find out the equation. Then if anything is required from the inlet condition, then we need to go like that. Or else you can go, if you know the steps like what you need to do, then we can go directly. But first we can find out the tangential velocity at the inlet and outlet condition. So that will be helpful in the future. That means first one we can calculate tangential velocity. So what is the tangential velocity formula? Now we know that tangential velocity of impeller at inlet and outlet condition. So inlet condition is, that is U1, and which is nothing but pi d1n by 60. So this one we can write pi value is keep it same, and this is 0.2, and this is 1200 and divided by 60. So this one we can just cancel it, that 6, and this is 20. So 20 into 0.2, that will be 4, and this will be pi. So 4 into pi equal to 3.14, then we'll get, this is 12.56. This is meter per second, and this is at inlet condition, correct? This is about inlet condition. Similarly, the outlet condition, what is the tangential velocity of impeller will be? That is U2. So in the U2, just we need to change the diameter value, D2 divided by 60. So here, so remaining all the values will be same. Okay, only if you see the value of diameter twice, here 0.2, here 0.4, remaining all are same. So what I'll do, without doing all these things exercise, I'll just make it double. Okay, so 12.56 into 2, so that will be 12.24. This is 56 means 112, near about 112 will be there. So 25.12 near about will be there. Okay, this much meter per second. So this is about the tangential velocity. First step we have completed. So here we got U2. Now we are targeting, you need to find out the value of VW2. So to finding the value of VW2 at the initial inlet condition, at least we can find out the value of, so here already VW1 is given 0. Okay, at inlet condition. Now at the inlet condition, any other value can be identified, so that will be helpful for the outlet condition. So here I can say that VF1 equal to VF2. Okay, VF1 equal to VF2. So if you are able to find out the value of VF1, so that will be helpful for to take the value in the VF2 at the outlet condition. So what I'll do, in the inlet condition, if you see theta value is given, E1 also known, and only VF1 is unknown. Okay, so what I'll do here, let consider the inlet velocity triangle. Inlet velocity triangle. Okay, and here I can write, this is tan theta equal to, I can write this is VF1 by E1. So here I can write VF1 equal to E1 value how much? This is 12.56, and this is 10 theta. Theta equal to how much is given? 20 degree given. So we can calculate this value. Yeah, this is 20 degree given. Let trigonometric of this multiply 12.56, 4.57. So here we got the value of VF1 equal to, here it is 4.57 meter per second. Okay, now the same value I can use in the outlet condition, because as I told you that VF1, that fluid flow velocity at the inlet equal to be at the outlet condition. Now again we'll go for the outlet velocity. At the outlet velocity triangle, the same thing again I am going to consider the 10 phi value. Okay, so 10 phi, so 10 phi equal to where? This is our 10 phi. Phi, angle phi is there. So what I can write here, like VF2 by, see here I need to write this value, actually this one, but this value is not given, correct? So what I can write, U2 minus VW2. So here I can write this is VF2 divided by U2 minus VW2, because any other angle if I consider, there I won't get the value of VW2. So by this method only I can able to find out the value of VW2. That's why I have taken this formula. So what I can write here, unknown is like, this is the VW2 part. So I'll take U2 minus VW2 equal to VF2 value. The same thing I can write here, 4.57 and divided by 10 phi. 10 phi equal to, that is nothing but 30 degree, correct? So now here I can write VW2. Okay, VW2, I'll take it to this side. U2 how much? This is 25.12, what we have calculated already here. Okay, and this minus 4.57 divided by 1030. So what I'll do, I'll just let me find out. Yeah, 4.57 here divided, bracket start, and this is how much? 30 and trigonometry of 30. So we'll get 7.918. So some value we got here, like 7.918. If I subtract this value from here, so near about I'll get 25 minus 7, 18, but here 0.9 is there, so we'll get 17 point something we'll get. Anyway, we'll just minus that value also. This minus 25.12. So minus 2 point, like minus 17.20. So I'll take 17.20 meter per second. So this is our velocity VW2. So now as per our requirement, we need to find out the work done value. So now work done by the impeller per unit weight of water. Okay, so that one we can write, this is VW2, that means 17.20 into U2 how much? 25.12 divided by G is nothing but 9.81. just you solve it, you will get the value of work done. Just I will multiply this 25.12 and divided by 9.81, 44.04. okay, this is 44.04, some 80 something is there. Okay, this much work done. So that is Newton meter per Newton we can write. Per unit weight is given, that's why it is coming Newton. Okay, so this is our required answer. Okay, so this is our required answer, what is given in the question. Now just let me highlight this. First thing, we need to identify the data given from the question. So once you identify the data given from the question easily, see, very simple question this is. D1, D2 easily can be identified. Then speed is given, and blade angles at inlet and outlet conditions are given, 20 degree and 30 degree. But before that, you should know about the diagram, because diagram is most important. At least if you know the velocity triangle diagram for the either turbine or pump, anything, impact of jets, we have studied many things. Okay, So we need to remember this velocity triangle, how it will be for the centrifugal pump. Then only you can identify like, okay, 10 phi, like this angle of what I have taken, this formula also required, tangential velocity formula also required. Okay. And at the inlet condition 10 phi, 10 theta, outlet condition 10 phi. So these things, how we can identify from this diagram only. Okay. So diagram is important. And finally, we know this formula, like as I told you, work done formula. So just we can put the value, you can find out the answer. I hope you understand this problem. Still, if you are having any kind of doubt and query regarding this, you can give a comment on that. Thank you.